Hi, and welcome to Tardigrade Thursday. Our topic today is security access, and I'm here with John Gleeson, Vice President of Operations. John, before we jump into the more detailed part of the conversation, what's the big idea that people should walk away with today?
Hey, thanks, Jocelyn. I'm really happy to be here on Tardigrade Thursday. I think a lot of people listening will be interested to learn about the ways the tools we built to ensure the security and privacy of the data stored on the distributed storage platform can also be used by the developers and end users of applications that are built to store data on our platform to help increase the security and the privacy of those applications.
I'm interested in talking a little bit more about the security and privacy increases of the applications. To really give that some context, it would be good to talk about the constraints that we had to work under.
Sure, Jocelyn. So there's a ton of detail on the constraints spelled out in the white paper that we use to sort of guide the development of the platform. But the main idea is that we had to build with the assumption that any node could be run by any person at all. And so we had to implement the zero trust security architecture based on the assumption that any of those people could also, by definition, be untrusted and potentially hostile. So this turns out to not only make our system much more resistant to attacks than traditional architectures, but it also gives us significant benefits in terms of the developers who actually end up building on the platform. These security and privacy capabilities that we've got are some of the most differentiating features. And they also give our partners and customers some really exciting new tools. We're going to talk a little bit about encryption, erasure coding, and the details of how we handle security and access management. But I think the number one takeaway here is that these things that we had to do to build the decentralized network in the first place to help people just store data at all really produced a unique set of tools for developers. And I'm excited to dive in a little bit more about how that's going to work.
Okay, yeah, I'd love to hear more about that. So maybe let's start there. Tell me a little bit about what we had to build to store and secure people's data in an environment where, as you just said, the majority of the infrastructure and all of the storage hardware is being run by other people and potentially hostile people.
Sure. So the network's really, a massive and sophisticated and complicated machine. There are a lot of moving parts, but the main things to understand when it comes to how we protect users' data are related to four key constructs. And mostly these are related to the fact that we are running a distributed network on other people's hardware. The first one of those things is encryption, right? And encryption is absolutely key to enforcing privacy. And we look at this as an end-to-end encryption process where only the end user has the keys to the encryption of their data. And that prevents any participant in the network, whether it's Storj Labs running a satellite, a community member running a satellite, or anybody running a storage node, from having access to any of the underlying data or the metadata about what's being stored. The second key thing is erasure codes. Erasure codes are used primarily for durability and performance, and that's where we get the redundancy on the network. And so the idea there is that it's the technology that's used in CDs and DVDs, where if you get a little scratch on the DVD, you can still watch the video. And we use that where if we lose storage nodes, the data still remains available. And while it's great for durability and performance, and resistance to sort of churn and failure in nefarious storage nodes, what it does is it happens to have an interesting security aspect too, because the data, every single file is distributed over at least 80 different storage nodes. The third construct is, of course, Macaroons and Api Keys. So we use these terms interchangeably, Macaroon and API key, and essentially the technology that we use to generate our API keys are something called macaroons. And what this does is it gives us a way to separate access management from encryption, because our privacy focus requires that we have strong access management controls, so only the right people have access to the right things at the right time. But at the same time, we need to manage that in a way where we don't actually know what's being managed, right? It ensures the privacy and security of that data. And the last construct that we've got here is something called an access. And an access is a developer-friendly construct that we've built. It's easy to use, but it gives developers the capabilities to use the access in parallel with encryption keys to make it easy to upload, download, and then, of course, share access to data. So at a high level, because we had to build these things to sort of manage access and maintain privacy, it produced sort of benefits and capabilities that developers can leverage. So on the encryption side, this whole end-to-end encryption piece, the way we ended up doing it actually provides a way for developers to use that encryption for sharing. And so we built this system whereby you have one encryption passphrase that encrypts all of your data, but you can derive little subkeys to share not only access to something, but the ability to decrypt it as well. And that first part, that access part, is actually done via those Macaroon-based API keys. And so we provided a system that, because we needed to delegate administration and authorization down to the client, it gives developers really flexible tools in terms of what they share, with whom, from what time frame, to really provide a great framework for access management. And then finally, that access construct that we developed to sort of make it easy to manage the parallel constructs of encryption and access management is a really powerful tool for building apps that share data in a really secure and private way.
There's 4 categories of things, and for each category, there's a concept, and then that concept yields a benefit. So the first one is the concept of privacy is handled with encryption, and then the benefit is that you get the end-to-end encryption, and that only the user is controlling all of the important pieces of, keys, privacy, security. And then the second concept is around erasure codes, and that is something that handles durability and performance. And then the benefits of erasure codes to handle durability and performance are the redundancy and performance, as well as security. The third one is Macaroons and Api Keys. And I think that maybe some people listening might want to just kind of keep it in their head that macaroons are what make API keys possible. And so we have this need to separate the access management from the encryption. And then the benefit of doing so is that you can then go ahead and delegate authorization, and you can centrally enforce that authorization that you've delegated. And then it's all wrapped up in the construct of access, like access with a capital A, which is what makes it all easy to use. And then the benefit of having that construct called the access is you're basically making it dev friendly. Does that track with what you're?
That absolutely.
So when we hear macaroons throughout, we can just kind of think API key.
Correct. Yeah.
Okay. We're starting in a really completely different place from most of the traditional approaches to data storage. And we both work here, so we're really close to it. But the difference that stands out is that we have this potentially hostile environment that's forcing us to build a different type of security model and addressing a really different set of threats than the set of threats that maybe have been assumed in the past. So I always think of it like we're training for a marathon in the Himalayas, like the way that runners will run at that really high altitude with the really thin air. And then when they come down to ground, it's like, oh yeah, I got this. So to dig down into the encryption aspect of this kind of deliberately starting in the harshest conditions before moving to more typical conditions. With end-to-end encryption, we're definitely providing the tools that privacy-focused developers need, but can you talk about how it works in practice?
Oh, yeah, absolutely. So the way we've implemented encryption is everything is encrypted automatically. And all of the encryption that we use is implemented using something called hierarchically deterministic, or HD keys. And what that means is that you have one encryption passphrase for all of your data, but every object on the network is encrypted also using the path for that data. And so each level of the path is actually derived from the path above it. And what that means is you can actually create child encryption keys so that if you want to share access to a particular asset, you can generate an encryption key just for that child asset and share it. So I guess maybe it would help begin from the beginning and talk about, sort of where this fits in sort of how we've implemented encryption from the top down. The most recent kind of best practice encryption standard is authenticated encryption. And our default configuration is AES 256 GCM and authenticated encryption. So in the architecture of our system, every time you upload an object, we actually choose an encryption key on the client side. It's under your control, but that encryption key is completely random. And that random encryption key is actually chosen sort of from a cryptographically random perspective. And then it's salted with a salt just to sort of eliminate any other variable that might get introduced into that process. And so what that means is that there's effectively no connection between how an object gets uploaded and anything else and the encryption key that gets selected. And so this randomized encryption key then is used to store your data. But the great thing is that it's stored on a per object basis. And so when you upload a really large object, a really large file, it's actually broken up into smaller pieces. And each and every one of those pieces gets its own randomized encryption key. And so this is sort of that concept of every object that's first broken up to a segment and then encrypting client side and then randomized and salted and encrypted. That whole layer of encryption layered on more encryption is designed to take your data and ensure that it's stored kind of like encrypted sand sprinkled on an encrypted beach. If I could mix that metaphor anymore, I would. But the idea is that because the network is potentially hostile and because we don't know anything about those storage nodes, it's extremely important that every single piece of that data remain extremely private and only available to the user that uploads it. And so I guess if you want to really think about how this is applied, the really interesting thing is that with the HD keys and the path used in the encryption process, if you know the root encryption key, which you do because you are the end user and we don't because we're the platform, and none of the storage nodes do either, you can derive any child encryption key at any layer of the hierarchy in any path where your data is stored. And so the way we're doing this is very similar to what Bitcoin uses for hierarchical wallets. It's not exactly the same because we also have paths in our data structure, but it allows you to share those subtrees, those subprefixes of the data, and it gives you the ability to give anyone access to just a small amount of that data to decrypt it without having to either re-encrypt it with a new encryption key or give them the keys to everything in your bucket. So even though the data is encrypted with one encryption passphrase and all your data can be decrypted with that key, it's really easy to generate subkeys from that specific path, and it's all derived. And so that means in real time, you can choose anywhere in that path and generate a key for it. And you can regenerate that same key over and over and over again because you know the root key in the path. And so there's no storing those keys or logging them or creating an access control list. Really, it gives us the ability to create rich access control and a sharing mechanism that allows you to break down aspects of your data into smaller sections. And so, a lot of people think of it as folder and path as a sort of a similar construct. They're not exactly the same, but in object storage, it's a good analogy. And so you can share just a single file or just a single folder if you want to, without any introduced complexity. Because again, the software that we produce handles all of that encryption and all of that child key encryption for you. And so I guess there is one trade-off where if you have all of your paths and all your file names encrypted so that our system doesn't have access to that path data, and that trade-off is that our system doesn't list your files in alphabetical order. Instead, it lists them in order of what the encryption passphrase names were sorted by. And so, some of the things that we're looking at in the future is to sort of re-expose and allowing users to choose whether or not they want to encrypt their paths as part of their metadata so that their paths can get returned in alphabetical order if that's important to them. But again, the most important thing for us is to make sure that everything is encrypted by default and that it's easy to maintain that security and also share what you need to share.
Okay, thanks. So that's the first topic that you had brought up, which is encryption. The second one you had brought up was erasure coding. Can you talk a little bit about that?
Yeah, absolutely, Jocelyn. It's important to remember that we do the encryption first before we do the erasure coding. And this is going to have a lot of knock-on effects into a number of aspects of the system down the road. Erasure coding is a way of introducing redundancy into file storage. And what we use is something called Reed-Solomon erasure coding. And it's a common erasure coding scheme. It basically gives us the ability to create a bunch of pieces of a file that have reduced redundancy baked into them. And then you only need a subset of those files, any subset, to get them back. So right now in production, we're using 29 of 80 Reed-Solomon erasure coding. And what that means is every file is broken up into 80 pieces. And to reconstitute the file, we only need 29 of those 80. And it's any 29. And so the cool thing here is that when you are uploading and downloading those 29 pieces and you reconstitute it from the erasure coded set, just the act of reconstituting your file is enough to verify that the file you're getting back is exactly the data that was stored. And that's why Reed-Solomon is so widely used. Reed-Solomon is actually a really old algorithm. It's used in CDs, it's used in DVDs, and it's the reason that those CDs and DVDs will still keep working, even if they've got a scratch on them. It's even used in satellite communications and a variety of other things. We're using Reed-Solomon mainly because it's well understood, it's fast, and it definitely solves our problem in a really good way. And we have a good library for it. A couple of problems that it solves are, one, when we upload a file and we store it across a wide range of nodes, it's possible some of those nodes can go offline. And even though those nodes go offline, the file remains highly available. And second, it also has a security benefit where those files are stored over a wide range of nodes, and to get all the pieces of a file without the actual access credentials, you have to go storage node by storage node, compromising different storage nodes on different networks with different security paradigms operated by different people, and try and get those individual pieces. And you've got to figure out over the thousands of storage nodes where the 29 pieces are that you actually need. And so it's more than just security by obscurity. Now, of course, as we're looking at how we use Reed-Solomon, not all the libraries support doing error corrections and things like that. Where if some of the pieces are slightly corrupted, Reed-Solomon can actually detect those and sort of manage around them. The library that we're using in Go was actually written by one of our employees, and it was figured out by the Berlekamp Welch error correction algorithm. And I don't know many other libraries that actually implement it in a way that allows us to do error recovery. With many of the Reed-Solomon libraries out there, they just kind of assume that there are no errors in any of the reconstituted pieces and hope for the best. But the expectation, you've probably done some research hashing your own to confirm, is that the pieces are accurate before you even download them. We're doing that sort of best of both worlds approach. And so one of the ways that we use this is through audits. And so to make sure that the storage node operators are actually storing the data that they are supposed to be storing, we can take small little pieces of any one of those encrypted pieces that's floating around the network, and we can verify the signature and confirm that the piece is actually the right piece, and that the storage node is storing it and it's still intact. And it's a pretty neat trick, because we can do that without actually having access to the contents of that file. So we don't need the encryption key, because it's encrypted first and erasure coded second, to verify the file is still intact. And so erasure coding then has both those benefits of redundancy. It has the benefits of durability. As storage nodes go away, it leaves us the ability to repair pieces on the network, but at the same time, it maintains the complete privacy of the file, and it layers in a security element.
Okay, thanks. So that brings us through encryption and erasure codes. I'd like to move forward and talk about macaroons and access. And I'd also like to cover some real-world examples to kind of, solidify the concepts for people. My first question to lead that off then would be specifically, what is a macaroon and what are the benefits that they offer?
Sure. So we use the terms Macaroon and Api Key internally kind of interchangeably, right? So the technology choice that we've made for our API keys is something called a macaroon, and macaroons came out of a Google white paper a while back. And it's basically, as you can guess kind of from the name macaroon, it's a species of cookie. And so effectively, macaroons are a cryptographic authorization credential. So
Are they
it's like a cookie, but it's got superpowers. It's totally a super cookie. We implemented macaroons as our API keys because one of the key things that we needed to do was separate the encryption aspect of data storage from access management. So we need people to be able to upload and download and do sort of the file sharing and administration in a way that separated out encryption, so that the platform and the storage nodes never see an encryption key. but you can still process access, fairly sophisticated access management credentials. But that means that, because we don't have the encryption keys and we don't know anything about with whom files might be being shared, and we don't want to, it means that we have to have a way to delegate authorization management down to the client. So the client needs to be able to figure out what's being shared and with whom it's being shared, but it doesn't. We don't want to have to ask the network and to give the network any more information it absolutely needs to handle that aspect of file sharing. And so we chose Macaroons and we've implemented them. And it's effectively this bearer credential that can be basically delegated to create additional layers of access. So Macaroons have some pretty good benefits, especially in a trustless environment like the Tardigrade network, in that developers building on top of the platform have the power to manage access, and they don't need to actually trust the Tardigrade satellite's ability to properly manage encryption keys. They can also be chained, which becomes really important when your use cases go beyond anything but the simplest sharing use cases. Macaroons give us the delegated access control so that the satellite doesn't need to be in the loop for that step. And when you append one macaroon to another, you get a totally new macaroon, but you don't get the original signature. So these are also sort of hierarchical in how they're developed. But unlike encryption keys, where the hierarchy is derived from the path prefix of the structure of the object storage and how you've stored the data, API keys have a different hierarchy, and it's derived from the relationship, the access restrictions. So HD API keys embed the logic for access that allows it to be restricted simply by embedding and sort of connecting those restrictions one to the other. And so we'll talk about an example in just a moment, but if I restrict access to just a single path in a key, I can take that key with a access restriction in it to a specific path and create a second new key with not only restriction to that path, but then a further restriction to a child path. And the big distinction there is that once I have that second key that's restricted to just the subpath, I can't go backwards up the chain. There's nothing I can do to muck about with that key that could let it be used further upstream. But that parent key will always have access to everything below it.
So control sharing is really fundamental to any file storage system. And fine-grained control is obviously very important to any of us using it in a practical way. I'm interested in that thing you just said about appending one macaroon to another, but first I'd like to hear a little bit more about the basic concepts. So to clarify for new listeners, I just want to note that satellites are the part of our storage network that know where all the pieces are. Satellites perform audits and handle repairs, but satellites can't see data and data doesn't pass through them. So it's very important that the encryption keys are handled correctly outside of the satellites.